Hey everyone, welcome to iTower. In today's video, we're going to dive into Dijkstra's algorithm for finding the shortest path in a graph. This is a crucial algorithm with real-world applications like routing systems, GPS, network optimization, and much more. It's essential to understand Dijkstra's algorithm whether you're preparing for a coding interview or working on projects that involve pathfinding. It's one of those algorithms that comes up often in both interviews and real-world applications, so mastering it is definitely worthwhile. Before we jump into the code, don't forget to hit that like button and subscribe to the channel. Your support helps the channel grow and ensures I can keep bringing you more content like this. Now, let's get started with Dijkstra's algorithm and break it down step by step. First, we'll define a function called Dijkstra that will take in two parameters, the graph and the starting node. The graph is an object where each key represents a node, and the corresponding value is an object containing the neighboring nodes and the edge weights between them. The starting node is where we begin our search for the shortest path to all the other nodes. We'll also need a couple of structures to help us with the algorithm. First, we create an empty object called distances, which will store the shortest distance from the starting node to every other node in the graph. Initially, we'll set the distance of every node to infinity, except for the start node, which will be set to 0 because the distance to itself is always 0. Next, we'll set up a visited set to keep track of the nodes that we've already processed. This helps us avoid revisiting nodes and recalculating distances for them. Finally, we'll initialize a queue that holds the start node. This queue will help us manage the order in which nodes are processed. Now, let's move to the part where we populate the initial distances for each node. We loop through all the nodes in the graph and set their distance to infinity, which means they are initially unreachable. Then, we manually set the distance to the start node to 0 because that's where we're starting from. After setting up the initial distances, it's time to enter the main part of the algorithm where the actual work is done. We enter a while loop that will continue running as long as there are nodes left in the queue. In each iteration, we process one node from the queue, starting with the start node. We remove the first node from the queue and check if it has already been visited. If it has, we skip processing it and move on to the next node. If it hasn't been visited yet, we mark it as visited, which means we've now processed it. Once we have the current node, we can look at its neighbors and calculate the shortest path to them. For each neighboring node, we calculate the new possible distance by adding the weight of the edge from the current node to the neighbor to the current node's distance. If this new calculated distance is shorter than the previously recorded distance for that neighbor, we update the neighbor's distance to this new shorter value. After updating the distance, we add the neighbor to the queue, which means we will process it in a future iteration. Once the queue is empty and we've processed all nodes, the distances object will contain the shortest distance from the start node to all other nodes in the graph. At that point, we simply return the distances object, which holds all the shortest distances. Now let's test our function with a simple graph. We'll create a graph where each node has some neighboring nodes with specific edge weights. For example, node A might be connected to node B with a weight of 1, and node B might be connected to node C with a weight of 2. We'll run the Dijkstra function and pass the graph along with the start node as parameters. The output should be an object with the shortest distances from the start node to every other node. Let's create the graph for testing. Here, node A is connected to B with a weight of 1 and to C with a weight of 4. Node B is connected to A with a weight of 1, to C with a weight of 2, and to D with a weight of 5. Node C is connected to A with a weight of 4, to B with a weight of 2, and to D with a weight of 1. Node D is connected to B with a weight of 5, and to C with a weight of 1. When we run our Dijkstra function with A as the starting node, the expected output should look something like this. This tells us that the shortest distance from A to B is 1, from A to C is 3, and from A to D is 4. So, in the end, we've successfully calculated the shortest path from the start node to all other nodes in the graph. And that's it! We've covered how Dijkstra's algorithm works and how to implement it in JavaScript. I hope this explanation helps you understand how it works under the hood and how you can use it in your projects. If you found this video helpful, make sure to give it a thumbs up and subscribe to the channel for more tutorials like this. Thanks for watching, and I'll see you in the next video.